All right, so we're going to continue this analysis, and where we left off last time was we had discovered the expression for the radial coordinate as a function of the azimuthal angle. So this is a polar coordinate system, and we have solved for this very interesting function, which is the shape of the orbit. And this is the shape of the orbit, and it is inevitably a conic section. And what's interesting is that the eccentricity of the orbit, which is what this term here is, this eccentricity can be can give us an ellipse or a hyperbola, right? Because it can be greater than 1, which would be, this term here would be, if this is a positive number, we could have something greater than 1, and we would get a hyperbola. And if this is a negative number, we would have an ellipse. This should be a K, by the way. The kappa, that's the strength of the potential. Sometimes I use a C there, and C is very common in the literature, and I get confused sometimes. So we have hyperbolic orbits, we have elliptical orbits, we even have, in principle, parabolic orbits if the energy is 0. So the energy can be positive or negative too. We'll discuss that and the nature of these potentials probably in the next lesson, because that, again, is something that we need to prepare ourselves to understand the Schwarzschild geometry thoroughly. We really have to understand this classical geometry, otherwise the Schwarzschild geometry doesn't become interesting. The key part of the Schwarzschild geometry is black holes can suck things in that the Newtonian system cannot. And in order to understand that, you really have to have a good grip on the Newtonian system, especially the effective potential. But we're almost there. I just want to make sure we go through the whole process and we develop this function, the radial coordinate as a function of time. And the reason this is an important thing to me is, first of all, it's an interesting classical calculation that's not typically done, but seems obviously interesting. It's not typically done because it's mathematically a little intense, although by the time I actually went through it myself and worked through some of the material in the books, it's in principle not that bad. But what it is it's a coordinate as a function of time, where time acts as a parameter, right? Time acts as a parameter, and this acts as a coordinate. And by going through this exercise, we understand how the Newtonian system treats time as this universal parameter from which all things can be calculated and measured. You tell me the time, and physics tells you the answer, which in this case is the location in the radial direction. Likewise, there should be a phi of t. You tell me the time, I tell you where it is in space relative to this azimuthal angle. Likewise for theta, which of course is a constant in our condition, but it's still the same thing. You tell me the time, I tell you where it is in its polar angle, right? So, well, in this case it was pi over 2, right? So that's the Newtonian concept, and exercising it, you really get a good, intuitive sense. I mean, you already do, right? Everybody has this intuitive sense, but so much so that we don't even acknowledge it. In other words, in our study of physics, if you've made your bones, or if you've studied any engineering physics or any elementary physics, you've always treated time as some kind of ticking parameter from which all things in the universe are calculated and measured. And the answer to just about every problem is, where is something in the future? You're predicting the motions of things in the future. So we should finish that exercise, and we should find r of t. We should do that. So we're going to do that. But also, doing this exercise gets us to the point where we actually realize what a revolutionary thought general relativity is, because now we actually, in general relativity, we're going to calculate time as a function of some other parameter, and r is going to be the function of some other parameter, and phi is going to be the function of some other parameter, and theta is going to be the function of some other parameter, where time joins the list of things you calculate along with the theory, and you've got to find some other parameter to measure time by. And that is the world line parameter, right? We've talked about already. And often the world line parameter is called the proper time. Well, we usually choose the proper time along the world line to be the parameter. But now that is no longer a universal time. That's just the time ticking along a clock that's moving along the world line. That's one guy's ticking clock. And so you're referencing all the universe, the coordinate time, the coordinate position, all through this world line parameter. And that is a revolutionary difference, really. That is really huge. And anyway, so without belaboring this much more, let's go ahead and think about this calculation here. So in order to move forward on this, we're going to start with phi dot, the constant of the motion term, right? Remember, phi dot was a constant of the motion. Here is that constant of the motion. And I'm writing it now in terms of u. This should be a mu, right? So remember, u was our substitution. Little u is our substitution, 1 over r. And so now I am writing phi dot, the constant of motion phi dot. I replace this 1 over r squared with u, so I get a u in the numerator. Then I take d phi dt and I just invert it to get dt d phi, which is a very simple calculus operation. You literally are going to inverse this and you get mu over u squared. So now this u squared is in denominator. Remember, h is the angular momentum. It's a constant of the motion. Mu is the reduced mass. So these are known quantities. So this part here is just a number. So this is the functional part, and we replace u squared with its functional form, which is this, right? Remember that from the r. This was 1 over u of phi, right? So if I flip this upside down, I get 1 minus this. This goes in the numerator, that goes in the denominator, which is what's going on here. This goes, well, it goes in the denominator of this object because u itself is just this divided by h squared. So 1 over u, which is 1 over u, which puts u in the numerator, puts this in the denominator. But it's u squared, so we've got to square this. And then when you work out the squaring of, whoops, wait a minute, I got a bracket problem. There, so it's this guy here squared. And then this mu here is that one there, this h is that h, this is 1, this is 1 over mu squared right in here. So I can take this square, use this constant, and I can simplify things a little bit to get this guy, which is just this constant. This is totally known. We know that. That's the strength of the potential, reduced mass, angular momentum, so that's just a number that we know. I'm now taking this guy right here. I'm taking this, and I'm just going to replace it with E. I'm going to replace it with E for the eccentricity, but again, it's a number we can calculate. We can calculate it right now because the problem itself is going to specify the total energy E, the total angular momentum, mu, and kappa, which is what this thing is, right? 1 plus that, the square. So all that is what we just call E. So it's just a constant. So I'm just renaming it a constant. So it's no big deal. So this is the thing, right? If we can integrate this, notice the variables are separated. This is all dt over here. This is all phi over here. So integrating this will give us the functions we seek. It'll give us time on the left and phi on the right. It could very well be a mess, but it's the answer. It's the answer to the problem. So the question is are you happy with this as being the answer, or do you want to actually find the answer? And this is a chance, I think, this is typical of the way I like to work is, yeah, okay, so this integral here is a Calculus 2 problem, right? But when was the last time you took Calculus 2, right? It's actually worth doing. And in fact, any chance you have to review some of that stuff is always helpful because it just, each time you study new material, you're not getting farther and farther away from the fundamental mathematics that you need to know. So it's worth executing this integral. I guess you could look this up on a table. You could do it in Mathematica. but it never hurts to do it, and that's what the rest of this lesson's, well, most of this lesson is going to be about, is executing this integral. So it's now a math review at this point. So how do we do this integral? Well, the first thing is we realize that this is a rational function of trigonometric functions. And in principle, all rational functions of trigonometric functions can be integrated using some technique. It's not always easy, but the answer is in terms of the elementary functions that we basically study in Calculus 2, which includes all the trigonometric functions, the hyperbolic functions, the inverse trigonometric functions, the exponential functions and logarithmic functions. It just excludes the elliptic integrals, the elliptic functions, which are elementary at a higher level of the word elementary. But we're going to find the technique to do this. It looks like it's simple. 1 minus e cosine phi quantity squared. That should be trivial. And it does show up in some more sophisticated charts of integrals. But this isn't a totally trivial integral. So let's begin and let's tackle this thing. The first step is the trivial left-hand side, right? We just, t minus t0 equals, and then this is our right-hand side. We're going to integrate from 0 to phi, and this will tell us, when we're done with this integral, we'll have a function of phi. The upper limit of integration will become the independent variable in the right-hand side, or a variable of the right-hand side. And by inputting phi, we should be able to calculate the time. So it'll be the literal way this is going to be written is time as a function of phi. This may not be invertible or trivially invertible, right? It may not be possible to turn this into phi as a function of time. It really depends on the functional form of this side. However, t as a function of phi is good enough for us because we could, in principle, make a table and calculate phi as a function of t from inverting the table with some arbitrary degree of precision. So we'll be happy with t as a function of phi if that's what we're indeed left with. Spoiler alert, that is in fact what we'll be left with. So with all of these things, we have to understand it's always about the clever substitution. And the substitution we want to use in this case is t equals the tangent of phi over 2. That's going to be the substitution that we are going to ultimately apply to this. Now notice that's not obvious. This isn't your standard substitution method of integration where we look for a function in here and a differential equivalent up here and make a substitution. This is a substitution that is not obvious at all. Fortunately, we learned it in calculus. Actually, this substitution I didn't learn in calculus 2. This is one level above calculus 2 substitution. We learned a lot of trigonometric substitutions that are important. I think we learned all of the things like 1a squared plus x squared and 1 square root of x squared minus a squared. We learned all of those substitutions, arctangents and tangents and things like and arcsines and things like that, which are important in our work with the Schwarzschild geometry. We'll see why those are important later. But this substitution we didn't learn. So what do? We have tangent of phi over 2. It's the half-angle substitution. The tangent half-angle substitution is what this method is called. So we begin with this half-angle identity from trigonometric, our list of trigonometric identities, which undoubtedly you do not have memorized, but it's easy enough to find. I feel like I don't need to derive trigonometric identities. So from here, we just solve for the cosine. The cosine of theta, we're sort of going to invert this whole thing. 1 minus, let's see, 1 minus 2 sine squared theta over 2, right? Not theta. Why am I using theta? This should be, well, this is just our generic identity, so I'll use theta. But now look at this clever thing. So cosine theta is 1 minus, and then ready for this, 2 tan squared theta over 2 times cosine squared theta over 2. And all we're doing here is understanding that tan squared of theta over 2 equals sine squared theta over 2 divided by cosine squared theta over 2, right? So this cosine squared here cancels with that and leaves the sine squared here just like that. So this is just a literal identity, right? It's just a literal identity. So that's easy. But now we execute this substitution here, and I'm going to write cosine theta is 1 minus 2t squared, right? Cosine squared theta over 2. And then I play around with it some more. These are all sort of, each step is straightforward and obvious. The totality of the logic is, of course, something some very clever guy did. But I convert cosine into, not cosecant, into secant squared theta over 2, which then goes 1 minus 2t squared over, and then I use the Pythagorean relationship for secant squared, which is 1 plus tangent squared. So that makes this 1 plus tangent squared phi over 2. And then, of course, I make this substitution yet again, and I get 1 minus 2t squared over 1 plus t squared. And then it's obvious we take this 1 and write it as 1 plus t squared over 1 plus t squared, and combine the two, put it all over a common denominator, and you get 1 minus t squared over 1 plus t squared. Okay, and that's what cosine theta equals. Phew. So our substitution, this substitution here, right, is tantamount to the substitution cosine phi equals 1 minus t squared over 1 plus t squared. So that's not obvious at all, but look what it's allowing us to do. It's allowing us to go in here and take this cosine term and turn it into a rational fraction of polynomials. And that we can definitely chew on and integrate. And then the last thing we need to know is we need to go dt d phi, right? That's going to equal, let's see, it's going to equal 1/2, and the derivative of the tangent is secant squared phi over 2, right? Is that right? I hope so. Phi over 2. Right, and then we use the same Pythagorean identity we used right here, and we get that equals 1/2 times 1 plus tangent squared phi over 2, and that equals 1/2 of 1 plus t squared, right? And therefore d phi equals 2 over 1 plus t squared dt. So whenever I see a d phi, I can substitute it with this, which of course is what's going to happen right here. There's a d phi, right? This d phi is going to get this substitution, and then we're going to use this substitution for that part. Well, actually, just this part. Okay, then we'll expand everything, and we'll have some kind of polynomial, rational polynomial here in t, which we can attack. Then there's the question of the limits of integration. I guess we should make that clear. If phi is, if phi is 0, the tangent of 0 will be 0. So the lower limit of integration here will be the same. This lower limit will stay there, and this will become just tangent of phi over 2. Okay, so let's make this substitution. And here is the substitution, right? I just took the du, and there's the du with the 1 over u squared and the 2, which comes from this. And the cosine phi, I put it right in here, and I've left everything else alone. So now what we can kind of see what's going to happen. This square is going to expand this guy out. This guy will come in, and we'll multiply, and we'll get some long fraction under here that we'll get some long rational expression under here. It looks like, this guy inside would actually cancel here. That's a nice effect. And then we'll have a big old polynomial in the denominator, and then we can start attacking that. Now, when I work this out, this is what I get in the denominator when I just sort of rotely expand this thing out, right? So you can kind of see what's going to happen. When I square this term here, that'll be a 1, so I'll end up with a 1 plus u squared term, which will contribute one of these. I guess that's what this 1 is here. And then, squaring this term, I'll get the numerator and denominator squared, but then this will multiply one term out of the denominator. So in order to clear that denominator, I'll multiply again by 1 plus u squared, which puts a 1 plus u squared in the numerator, right? So once I've done that, you start getting this proliferation of terms. But it comes up that there's a coefficient times u to the 4th, a coefficient times u squared, and a constant coefficient. And those can actually be simplified a little bit. And here I've done the simplification. This obviously is 1 plus e squared. This is 1 minus e squared. This is still 2. This is the same thing. And then finally, I guess my final form will be, and this is my final form. I guess I should say at this point, why do I have a u here? Oh, crap. So I guess my initial substitution was, you can see I intended to do t equals tan phi over 2, but somehow I slid into this u. So I've got a u here everywhere. Sorry. So this is now u. My substitution, I'm just using a different substitution variable. I'm going to use u. The reason I don't really want to use u is because I've already kind of used u for that substitution earlier in the analysis part of this. Now this is just purely a mathematical substitution. Whoops. U equals 0. So now I've kind of gone backwards. In other words, just to be very clear here, the substitution that I'm actually doing now is u equals tan phi over 2. But this u here, right, is completely unrelated to the u from the previous lecture, this u here, right? That's not the same u, right? That we still have, that u's long gone. This is gone because we have r as a function of phi there. So that's all good. Now we have, this t here is actually time. So I guess my substitution for t was also kind of redundant, right? When I was going to argue this substitution when I had a t here, that wasn't supposed to mean time either. This t is not supposed to be time. This t is just a mathematical substitution. I guess I'm not creative enough to put letters down on the fly. So now I'm replacing t with u, which is also overloaded because I've used u previously. But anyway, I think you guys can follow. This is just elementary. Well, I shouldn't say elementary calculus. This is intermediate calculus. All right, so this now is our integral. It's a polynomial in u, right? And basically you notice that this is, it looks like a quartic in the denominator, but it's actually a quadratic, right? Because there's no u term. There's no u to the first power term, and there's no u to the third power term. So it can be reduced to a quadratic, and indeed this is the quadratic it reduces to, and we're lucky that it reduces so nicely. There's no reason to suspect that it would, but it does. Now you might be in a rush to find the roots of the quadratic, and it's not hard. You can use a quadratic equation and do that. But we're going to go with partial fractions. Whenever you see this, now you're thinking, oh wait, I know this. This is a partial fraction situation. So how do you solve this with partial fractions? So here's our integral. Now remember, for partial fractions, what we do is we take this denominator, and every conceivable factor of this denominator is going to be strung out as a sum. But in this case, the denominator is already factored, but it's a square factor of a polynomial. So you have to go back to your I'm not going to totally review the actual method of partial fractions, but I will execute it. So I'll show you the first step in the resolution of this. And it goes like this. And the way that looks is this is broken down into partial fractions will have this form. Now you remember, if you have a quadratic in the denominator, some power of a quadratic in the denominator, the procedure for partial fractions tells you have the first power of that quadratic gets its own little partial fraction, and the second power of that quadratic gets its own partial fraction, and it would get the third and fourth. If this was a higher power, it would have one for every power less than this exponent in the denominator. In our case, it's 2, so you just have 2 terms. The numerator, when you have a polynomial, when you have a quadratic in the denominator, a quadratic factor in the denominator, the numerator is always a linear factor. An unknown constant a times the u, which is the linear term, and then a constant term. For both expressions, it's the same. Even though the power of the denominator is going up, the numerator expression is the same. If this was not a quadratic down here, you would only have the constant term. So this is the partial fraction decomposition, and now it's our duty to calculate a, b, c, and d. And the way you do that is you clear this of, you basically set this here equal to that here, right? So I take this on the left equal this, and then I clear this denominator by multiplying both sides by this denominator, which clears this denominator here, so you're left with cu plus d, but it only clears one term of this one. It clears this denominator too, but it leaves behind 1 power of itself up top. And so this expression here equals this expression here, and now you equate like powers of u. So, for example, the u to the third power term, u squared, has to be 0. And the only third power term is au times 1 plus e u squared. So we learn right away that au times 1 plus e must equal, well, there's no term over here, so that's got to equal 0. So that immediately implies that a equals 0. That was easy. Likewise, we can do this analysis for the linear term, right? There's no linear term over here. So whatever is linear in u here has got to end up equaling 0. But au go by u squared here is not linear, but au times 1 plus e is linear, but a is already 0, so that doesn't count. B doesn't develop a linear term at all, right? But C is linear, and C and D doesn't develop a linear term. So you've got to get CU equals 0, which implies C equals 0. So that's nice. So right away we know that's gone, and that's gone. And then we just have to solve for B. So let's look at that. So the term for b, let's see, if I multiply through, I get b times 1 plus e u squared, and that has to equal 2u squared. And b times 1 minus e, the constant term, that plus d is the only other constant term, has to equal 2, which is the constant term over here. This gives us, let's see, it gives us b equals 2 over 1 plus e, and then that means, now if I substitute that in here for b, the 1 minus e, 1 plus e times 2, I guess that's 1 minus e over 1 plus e times 2 plus d equals 2. So what do I do now? So I have to say d equals 2 times 1 minus e over 1 plus e, right? Something like that. That is, let's see, d equals d times 1 plus e equals 2 times 1 plus e minus 1 minus e. So I get d1 plus e equals, let's see, oh, this is going to work out nice, right? This is 2 minus 1. 2 minus 1 is 1. 1 plus e, 1 minus e is 1. So I think it's, oh no, I need another 2, another factor of 2. So there's a factor of 2 here, right? So it's this thing, right? It's 2 plus 2e minus 2 minus 2e. So the 2's cancel. That adds up to 4. So d equals 4e over 1 plus e. Phew. Okay, so now I know everything I need to know to substitute up here to get the partial fraction expansion of this integral. And let me write that down now in its full expression. I guess I'll do that on another page. So the initial substitution is pretty easy to see. We just substitute, for b, 2 plus 1 over e, for d, 4, 1 over e. This is a constant, right? These are constants, so the 1 over e will just come out front, and we can simplify everything a little more. And this is that simplification. Now here, I pulled out this 1 over e and 1 over e. I got that out here. But then I took the denominator and I divided by 1 plus e to get a u squared plus squared term. So the idea is I want something that looks like u squared plus a squared, right? Because I know that my standard integration techniques are very good with those particular types of terms. So that's what I've done, is I divided by 1 plus e, so I have a u squared, and then this term will be 1 minus e over 1 plus e square root squared. So I know it looks like a square root squared, but that's because I'm ultimately trying to get something I can just work my classic trigonometric substitutions for. And I did the same thing here because they both have the exact same structure, but this time I have a square there. And in order to make this work, I end up with a 1 plus e in the numerator squared, and then a 1 plus e here. So in other words, if I took this, put it in the denominator, and pushed it through, I would end up with this. And if I took this squared part, put it in the denominator, pushed it through, I'd end up with this. So I'm just rearranging things. There's nothing more than rearranging things. And now I'm just going to use some standard, much more common trigonometric substitutions from standard calculus, one of which is more common than the other, but the bottom line is both of these integrands, both parts of this integrand can be easily integrated. Remember, the numerator, this is just a constant, right? So I'll break this integral into 2 separate integrals and pull the constant out of each one, and in so doing, execute the integral, and we'll be done. So here I'll just show you the 2 integrals we're going to use. This integral here, everybody should know, or not. I've got to be careful. Everybody has at some point studied in their Calculus 2 class. This is every Calculus 2 class has that integral and develops it and proves it. I couldn't tell you right now exactly how to execute this integration, but there's a basic technique that gets you it. But the principle here is that this is usually something you have to memorize for some Calc 2 test. This integral, right, which is the same as this, but this denominator is squared, is not something that we routinely memorize, but is found on almost any semi-substantial table of integrals. Executing this integral is not hard. It involves the process of completing the square, which is a technique that you learn, but here it's just done in the table. So I feel like I don't need to take apart these 2 integrals. I feel like this is sort of the bottom of the recursive procedural tree of doing the integration. I felt like reviewing this substitution, this actually is interesting because we don't typically do it in calculus classes. So understanding this substitution and exercising it, that's worth doing. going back to the partial fractions and remembering the procedure for partial fractions and then going through this analysis, that's kind of worth doing. So everything is worth doing, but now I'm going to actually lean on, okay, this is elementary calculus. We can do this. Okay, so this integral is going to solve this one, right? This is, this is exactly, this part here is exactly in this form where a is the square root of 1 minus e, 1 plus e. And likewise, this piece here is exactly in this form with the same a, by the way. So let's execute that integral. And this is my calculation, substituting in the epsilon, working all of this out, putting a squared and substituting u for x, and this term here, 1 minus e, 1 plus e root for a, raising it to the third power gives you this guy down here after some, it's actually a lot of algebra. It's a lot of algebra to get to this. And that's not even the tightest expression of all of this, but it's a lot of algebra to get here. And then you implement this, well, it's a lot of algebra to get to that spot. But once we're at this spot, now we have to go back and replace u with tangent phi over 2, right? Which is sort of undoing these limits of integration. So we're going to go back to integrating over phi from 0 to phi. So making that substitution puts a tangent phi over 2 here, a tangent squared phi over 2 here, a tangent phi over 2 here, a tangent phi over 2. So you have an inverse tangent of a tangent, but you have this factor in front, so you can't just simplify it. So it actually is going to become a mess, and you can see why you're not going to be able to easily invert this. But now let's make that substitution, and what do you get? And this is not a hard substitution to make. You literally are substituting back for u in all of these places. And now we will try to keep, now it's just, this is the answer. I mean, you're actually done, right? Because tangent of 0 is 0, so this term goes to 0. The argument of the inverse tangent goes to 0, but the inverse tangent of 0 is 0. So this whole thing is 0 at the lower limit, and at the upper limit you just put in phi. So all I really need to do is erase this, and that is equal to, essentially it's proportional to t minus t0, right? So that's our function of t of phi, really, because it looks like, phi is buried inside this mess, and inverting this would give you phi of t, but you can't really invert it. You can get t of phi, however. But the point is you can actually simplify this significantly. And what I'll do is the basic way of simplifying this is you write tangent of phi over 2 equals 1 minus cosine phi over 1 plus cosine phi. Or that it also equals sine phi over 1. Wait a minute. Square root, right? Square root, and then sine 1 plus cosine phi, right? So you have those two things, and if you make this substitution, you put that here, you square this, and you put it there, and then I think you whoops, I wrote something wrong here. This doesn't make sense. Hold on, let me see what it is. Okay, yeah, I see what it is. This is a square here. Let me put the correction. That's a square there, so that's a square there, right? that lengthy algebra I was so proud of. I screwed it up here. But that's a square up there. So this ends up sort of being and that's how this 1 plus epsilon comes out, right? Or the 1 minus epsilon. No. So this ends up being 1 plus e u squared, right? Anyway, that's a square there, that's a square there. So you substitute this squared, so 1 minus cosine phi, 1 plus cosine phi here and here. So this guy gets substituted there and there. This guy, which is equivalent, gets substituted there. You're actually going to leave this alone. There's no reason to break that apart. But when you do those substitutions, you ultimately end up with a much simpler answer after a lot of algebra. And I'll just write down what that answer is. And this is the answer. This is the answer. T minus T0 times that factor. These are all known numbers, right? Angular momentum, reduced mass, strength of the potential, time. Then this is the azimuthal variable, and eccentricity is known. We know the formula for that. The square root of 1 plus, and then there's that fraction involving the same thing plus the energy, the total energy of the system. So the constants of the motions are all buried in the eccentricity. There's explicitly the constant of the motion is there. The eccentricity has both constants of the motion buried inside it. But everything is a constant except for this variable here and this variable here. Now, I promised phi is a function of t, but really this is t is a function of phi. And now r as a function of t is going to be, we have r as a function of phi, and so r as a function of t is going to be, we take this guy and push it in there, and we get well, let's see, we would need to invert this guy, right? We would need to invert this, right? So it's still very, very hard, right? So we can have r of phi of t is r of t. Now we don't explicitly have phi of t because inverting this is well, it's impossible, right? As far as I know. So but we have the means of actually doing this calculation. We have the means of struggling through this, finding the time corresponding to each angle, and then creating r of t. But you can see it's not trivial. I realize, my math is, I've skipped a lot of algebraic steps, but you can fill them in. This final answer you can check with Corbin and Steele, Classical Mechanics, Dover, page 97. That's where this final answer appears. They, however, don't actually do the integral. They just offer the expression, and they don't tell you what a bare the integral is. Okay, so that is basically our idea of how to develop these things as functions of time. The last thing I would like to talk about is the nature of this effective potential and how to interpret the meaning of the effective potential. But actually, I'll keep this one a little shorter, and I'll do the effective potential as another second short lesson. Maybe I'll get that one done very soon. Okay, so we're moving through our classical study here, and that lays the foundation to help us understand the Schwarzschild's geodesic solutions. So next time we will study the effective potentials in preparation for understanding the orbits around the Schwarzschild geometry and seeing how significantly they are similar and how significantly they are different from the general relativity solution. Okay, I'll see you next time.